Hello and welcome to the next video on the series of modern physics. We will discuss X-rays in this video. So X-rays are a part of electromagnetic spectrum. They have a very high energy, more energy than ultraviolet rays, and it was first discovered when high-speed electrons were made to fall on a metal surface. So we have electrons, and when electrons fall on the metal surface, X-rays were produced. So one of the first devices to produce X-ray was the Coolidge X-ray tube. This has a filament which is heated, and then we have a metal sheet here, and this metal sheet is cooled by flow of water. So when we pass current through this filaments get heated up. The filament gets heated up, and when the filament gets heated up, electrons are released. So release of electrons when we heat a metal is called thermionic emission. This is one important term or definition, thermionic emission. So the term thermionic means it has something to do with temperature. So whenever we heat a metal, though the electrons in the metal, when we heat them, they gain energy. Correct? We know that whenever we transfer, they vibrate more rapidly and they gain energy. And if we heat them sufficiently, the electrons will be able to overcome the nuclear attractive force, and they will come out of the metal surface. So this phenomenon is called thermionic emission. So this phenomenon of thermionic emission is used to generate these electrons. And now also note that there has been this arrangement has been connected to a battery like this. So this is connected to the negative terminal of the battery, and this metal is connected to positive terminal of the battery. So that means there is a potential difference. This is a positive plate, and there is a potential difference between the filament and the metal surface. And even if the electrons are released, say at zero velocity, they get accelerated towards the metal plate, and in this acceleration they will gain, or it is designed in such a way that they gain sufficient energy so that X-rays are produced. So this is the basic construction of a X-ray tube, or more specifically a Coolidge X-ray tube. And in the right hand side you see a profile of the X-rays which are generated. Okay, so in the right hand sides we have the number of, so suppose if in the x-axis we have the wavelength of the X-rays. Okay, so suppose we detect this X-ray and measure its wavelength, then we detect this X-ray and measure its wavelength. We detect this X-ray, we measure this wavelength. We detect this X-ray and measure this wavelength. So for a certain period of time we keep on doing this process, and we plot the number of X-rays, the number against the wavelength. Okay, so how many 100 picometer wavelength we measured, how many 200 picometer wavelength we measured, how many 300 picometer wavelength we measured. So we plot them in graph, and the distribution is something like this. Okay, so we see here that here it is pretty continuous. Correct? So these wavelengths are called continuous X-rays. Okay, but certain points we have unusually high number of X-rays. Okay, for example this and this. Okay, so these are nomenclated. These are sometimes given nomenclature. For example, K alpha for the first one is the K alpha, then K beta. Okay, K beta, and so on and so forth. So these are known as, for which we get a very high number, unusually high number of X-rays which corresponds to these wavelengths. They are known as characteristic X-rays. Okay, So let us see why we sometimes why we have a pattern like this. Okay, why we get a continuous, what is the cause of what is the cause for getting this profile of X-rays. Okay, so let us study that. Okay, so this is an atomic structure. Say this is n is equal to 1, 2, 3, orbital number 1, 2, 3, etc. Okay, so sometimes this 1, 2, 3 is also denoted by the letter K. So the first is known as K orbital, L orbital, M, N, O, P, and so on and so forth. So instead of numbers, these orbitals are sometimes denoted by the letters K, L, M, N, O. Okay, so these orbitals have electrons in them, correct? So these orbitals from Bohr's model, which we studied last video, they have electrons in them. So when these are this is the atom of the metals. Okay, so this is one of the atom of the metal sheet. So when an electron goes and collides with one of the electron, so suppose due to thermionic emission this electron is released and it goes and attacks this or it goes and collides against this electron. Okay, so the two things are possible. First thing which is possible is they collide, okay, but it doesn't have sufficient energy. It doesn't have sufficient energy to take this electron out of this orbital, or the angle is such that it cannot transfer sufficient energy to transfer this electron from this to any other orbital, or maybe even take it out. Okay, so what will happen is when it collides, okay, some energy might be lost or all of the energy might be lost. Okay, so suppose what first case is this electron collides with this electron, and suppose the energy of the colliding electron is E. Okay, so the energy of this electron is E. So it can lose energy after the collision. This can lose energy, and the loss of energy can be in the range of 0 to E. Either it can pass right through, correct, without losing energy, or it can strike and lose a maximum energy up to E. Okay, so that loss of energy will be converted as a photon or electromagnetic radiation which is coming out. Okay, so what will be what is the relationship? We know that what will be the energy. So what is the maximum possible energy? The maximum possible energy which can be transferred is E is equal to, which is E is the maximum possible energy which can be transferred, and we know that what the relationship between the lambda. Okay, what we are mainly interested in, we are interested in what will be the lambda of the photon which is emitted, correct? So lambda of the photon can be found out by the relationship E is equal to hc by lambda. Okay, correct? So if E is maximum, so if all the energy is lost and everything is converted to this photon, then E is maximum, and because lambda, so for this to be maximum, lambda is a minimum. Okay, correct? So there is a minimum lambda which will be emitted. Okay, and if energy is less, this lambda will, the loss of energy is less, this lambda will be more. Okay, so because E varies from 0 to E, lambda will vary from, or minimum lambda minimum to, if E is 0, if E is 0, then lambda have to be infinity, correct? A very large number. Okay, so if E varies from 0 to E, then lambda will vary from a lambda minimum to some infinite value, correct? So this is what is the continuous wavelength. Okay, so here you see lambda varies from one lambda minimum. Okay, so this is lambda minimum, okay, to a value which is, it almost will go and meet infinity at infinitive. Okay, so this is the fundamental reason behind the, or how this continuous wavelength from lambda min to lambda is equal to infinity is generated. It is again just a conservation of energy. Now let us look into why. So we have looked into how continuous X-rays are produced. Now let us look into the reason for why the characteristics X-rays are produced. Okay, so the first possibility was this electron collides with this electron, nothing happens to this electron, and some energy is lost, some or all energy is lost, and that is liberated as a photon. Another possibility is that when this electron goes and collides with this electron, it transfers sufficient energy to this electron which is rotating in the orbital, and that energy is sufficient to take it out. Okay, so take it out of this, it will put it out of its orbital. So what will happen? Then there will be a void or vacancy in the lower orbital, correct? So if this colliding electron has sufficient energy to knock out this electron, and this electron goes and escapes, then there will be a vacancy in this lower orbital, and this vacancy will be then, or can be then, fulfilled by any higher electron which is in the higher orbital. So a higher orbital electron can come down and occupy this lower energy state. So when a higher orbital electron with higher energy goes and occupies a lower energy state, okay, so the difference in energy between these two orbitals will again be released as electron, photon, not electron. The difference of energy when an electron migrates, or electron pops from higher orbital, it goes from higher orbital to lower energy orbital, it will release the extra energy in the form of a photon. Okay, so I have drawn this. K orbital is the lower orbital, L is the higher, M is the more higher. So suppose if K orbital electron has been released, has been ejected or put out by this colliding electron, then an orbital from either L can come here, L can come to K, or from this orbital it can come to K, or electron from this orbital can come to K, or electron from this orbital. Okay, so this is known as K alpha. So what I was writing here, so K alpha, K beta, and so on and so forth. So this will be K alpha, K beta, K gamma, and so on and so forth. Similarly, if an L electron is knocked out, then an electron from a higher orbital, say M, can come to L, or from this orbital it can come to L, or from this orbital it can come to L, correct? So these are known as, these orbitals are known as K alpha, these X-rays, characteristic X-ray will be known as K beta, L alpha. Now it is coming to L. So L alpha, L beta, L gamma. Similarly, there can be M alpha, M beta. Okay. So I think this pretty much. So what will be the lambda? Okay, what will be the lambda of this K alpha? Okay, what will be the lambda of K alpha? Lambda of K alpha will be equal to, we know that E is equal to hc by lambda, or lambda will be equal to hc by E. Okay, so what is the energy given away? What is the energy given away when it comes from L to K? The energy given away from when it comes to L to K will be equal to the energy of L minus energy of K, minus energy of minus energy of K. Correct. Similarly, what will be the lambda when it comes from M to K? So it will be lambda for K beta will be equal to HC by E M. It is coming from M to K, E M minus E K. Okay, so these are some of the theory of and definitions of X-rays. Not these are just the applications of the concepts which we have learnt in last classes, and nothing much new. One thing is, another small definition is hard and soft X-rays. So hard X-rays are X-rays with higher energy. These are relative terms. So high energy X-rays are called hard X-rays, and low energy X-rays are called soft X-ray. Okay, so we know that E is equal to Hc by lambda, or lambda is equal to Hc by E. Okay, so hard X-rays, because they have more energy, will have lower lambda. So hard X-rays are the X-rays with lower wavelength, and conversely soft X-rays will be the X-rays with higher wavelength. Okay, so with this we come to the next topic of our X-rays, okay, which is Moseley's law. Okay, which is Moseley's law. Again, Moseley's law is a very important, means actually this is a Moseley's law is quite old, but I wanted to discuss it in a little more detail, because it involves some derivations which will help to clear up some of the fundamental concepts. So that's why I like discussing this Moseley's law. This is also included in your CBSE or ICSE syllabus. So let's go ahead and discuss quickly what is Moseley's law. Okay, so Moseley's law states that the frequency of the X-ray is related by this formula, where A is a constant, Z is the atomic number of the element. We'll just discuss what element we are talking about, and B is again another constant. Okay, so Moseley did lot of experiments with different type of metals here, so metals, and he generated X-rays. So he bombarded with electron, and then X-rays were produced, and we know that X-rays produce one continuous X-ray is produced, as well as some characteristic X-rays are also produced, which are known as K alpha, K beta, etc. We just studied that. Okay, X-rays. So he studied the frequencies of these characteristic X-rays for different type of materials, for different metals. Okay, he studied that, and he found out that the frequency of these characteristic X-rays follows this law, where this law is square root of the frequency is equal to A into Z is the atomic number of the element, atomic number of the metal on which the electrons are falling and which is generating the X-rays. Okay, so if we plot frequency, square root of frequency against the atomic number, we get a straight line. Okay, we get a straight line, and this is the Moseley's law. So let us quickly discuss why derive this Moseley's law. Okay, let us quickly derive this Moseley's law, which is a good exercise, and I personally believe that doing lot of derivations clears up our concept. We can do derivations only when our concepts are very clear. Okay, so let us derive that. Okay, so we know that we have an atom, we have atoms, and this is the first level, this is the second level, okay, this is the third level, Okay, so suppose when this electron goes and collides, we know that characteristic X-rays are produced when it knocks out this electron. When it knocks out this electron, and an electron from a higher level goes to take this position, correct? So we have just studied this. So now we had studied the derivation of Bohr's energy, correct? So the Bohr's energy levels, we have just studied that lambda, we had just derived lambda will be equal to hc divided by ek, or let us write not in terms of lambda, because now we are discussing in terms of frequency. We know that the energy relieved, the photon, the energy of photon relieved is h mu, and it will be equal to the difference in the energy. So I will write it as, say, Em minus En. Suppose the electron is going from Em minus En. Okay. So suppose this is the mth level and this is the nth level. So the h mu will be equal to Em minus En, or I can write it as mu will be equal to Em minus En divided by h. Okay, so what is Em and En? So we had studied this, correct? We had derived in our Bohr's law that energy of an mth level or an nth level here, energy of nth level is given by z square ke square me divided by 2h square n square. This we had derived in our last class. Okay, but if you remember very clear, if you had concentrated on the last video, you might remember that I had told you one limitation of Bohr's law, that Bohr's law is applicable only for nucleuses with only one electron. Okay, only one electron, that is Bohr's law is applicable only for nucleuses with only one electron. Okay, so why is that it is applicable? These formulas are applicable for nucleuses with only one electron. For example, hydrogen atom or a helium, a positively charged helium, all these have only one electron. Why it is applicable only for one electron? It is because suppose there are two electrons here or three electrons here. Okay, so we had derived, the derivation was based on the principle that, if you remember, the centrifugal force mv square by r is equal to the Coulomb's force, and Coulomb's force for the charge was Ze here. Okay, the charge was Ze here. Okay, and of the nucleus, where Z is the atomic number of the nucleus. Okay, or atomic number of the atom. So the Coulomb's force would be equal to k q1 q2 by r square, correct? And q1 is Ze, q1 of the nucleus is Ze, and q2 or the charge of the electron is E. Okay, so that's how we got the Coulomb's force equal to this value, which is Z into k Coulomb's constant into E square by r squared. Okay, so but if there is another electron inside this, okay, another electron present, then this will also exert a force on this electron. Okay, correct? So the net force on this electron will no longer be equal to only the force of attraction between these and this, but this electron will also have an influence on the total Coulomb's law. So that is why all this derivation for Bohr's law is only applicable if there is no other electron. If there is another electron, then the Coulomb's force due to this electron also comes into picture. Okay, so suppose, but here all this Em minus En, we actually require, these are all metals like zinc, iron, etc., which have lot of electrons. Okay, so if we have to apply this formula, if we have to find Em and En, we have to apply a correction factor to this. Okay, so we have to apply a correction factor to it. So suppose I have a nucleus, okay, and an inside orbital has, say, any general b number of electron, all the inside have b number of electron, and outside is the outside orbital electron has been knocked out, okay, and an electron from a higher level is coming to occupy this position. Okay, so an electron from higher level, which is blue in color, suppose I am denoting in blue, this has come to occupy this position. So what is the net electric force experienced? So this is Ze, correct? Ze is the charge on the nucleus, Z is the atomic number. Okay, so what is the effective charge here? Effective charge inside, so suppose I am applying the Gauss law. So what is the effective charge inside this? So effective charge inside this will be now Z minus B into E. Okay, the Z minus B into E is the effective charge here, correct? So the effective Coulomb's force will no longer be Z K E square by R square, but it will be Z minus B, where B is the total number of electrons inside this orbital. Okay, so it will be about Z minus B into E square by R squared. So if you go over this full derivation again, okay, what will, same thing. So here V will be, instead of Z I have to replace it by Z minus V. Okay, similarly E is equal to half mv square minus, instead of Z I have to replace it by Z minus B. Okay, and finally if I do all these things, this En will be basically, instead of Z square I have to write Z minus B squared. Okay, so this formula I can write it as minus 13.6 into, instead of Z square by N square I will write Z minus B whole square by N square. Okay, so if I just substitute this value, okay, what will be Em? Em will be minus 13.6 Z minus B square by M square, and what will be En? En will be minus of Em. So I am writing this term. Okay, let me write it very clear. If I just substitute, okay, E is equal to this. Okay, if I just substitute here in this equation, I will get nu is equal to, if I just do some simple algebra, I will get 13.6 by H Z minus B squared into 1 by N square minus 1 by M squared. Okay, so if I take a square root on both sides, I will get square root of mu is equal to square root of 13.6 by H Planck's constant into 1 by, sorry, it will be 1 by N squared minus 1 by M squared, and under root of square root of Z minus V will be just Z minus B whole squared. Under root of Z minus B whole squared will be just Z minus B, and this term I can write as a constant A. So square root of mu will be equal to A. I will replace this by A Z minus B. So this is an important derivation. It's an interesting derivation because it clarified or helped us practice lot of concepts. So that's the reason why I particularly like this derivation. It helps us to explain a lot of modern physics concepts. Okay, so this is Moseley's law. Next and the last topic on X-rays is the Bragg's law. Okay, so we know that X-rays is nothing but photons. They are they come in the spectrum of electromagnetic radiations after ultraviolet rays. So X-rays are nothing but light rays of high energy, very high energy, and we know that light behaves as particle as well as wave. Okay, so if it behaves as wave, light behaves as wave, that means because X-rays are also light rays of high energy, X-rays will also behave like waves, and whatever behaves like wave, they will show under certain circumstances the phenomenon of interference, diffraction and all. Okay, so that's why X-rays particularly also shows diffraction, because they are also waves. But we had studied in optics, or we know from optics that for diffraction to take place, the aperture or the slit of the diffraction plate, the width should be very, very small. It should be of the order of wavelength of the light. Okay, so for X-rays to undergo diffraction, we know that X-rays are X-rays have very high energy. So if any object, any wavelength has very high energy, okay, that means its wavelength has to be very small. Okay, and now if wavelength is very small of X-rays, then for diffraction to happen, the slits should have very, very small wavelength, small aperture. Okay, or the split length should be very small. And in nature we find this in crystals. Okay, if naturally occurring crystals, these are the molecules, and the separation between these molecules are very small. In the molecular level, it is of the order of the wavelength of X-rays. Okay, so if we pass X-rays through the crystal, if we project X-rays through to the crystal, say I project them at an angle theta, then they will, because these slits in the atomic level are very small, they have a chance of or they can exhibit diffraction. Okay, and another important thing is, in diffraction we know that we have some white constructive interference where we get a bright spot, and we have dark spots where we get destructive interference. We can have constructive interference, we can have destructive interference. So the reflected light waves can either have a constructive interference and we can have bright reflected lights, or we can also have destructive interference and we can have no reflection at all. Okay, if they get all destructively interfere, or the waves cancel out each other, if the waves cancel out each other. For a detailed look at diffraction and what is interference, what is diffraction, how we combine two waves, you can study more about wave theory of light in your optics. But this is not the place to discuss them in much detail. Here we are discussing just the basics of Bragg's law. What is Bragg's law? So I will not go into details of how we add waves and subtract waves at this place. But in essence, these different X-rays, after getting reflected from different layers, okay, either they can constructively interfere or they can destructively interfere. Okay, and we know that what is the condition for constructive interference. You can go back to your waves and revise what is the condition of constructive interference. Okay, so constructive interference means I want some light to get, I want to see a bright light reflected or bright X-rays reflected from this. So for that I have to have a constructive interference, and the condition of constructive interference between any two waves is that path difference delta x should be a multiple of n lambda. Okay, so it should be a integral multiple of the wavelength of the light. So for constructive interference, for these two waves to combine in a constructive manner to add up, the difference in path length, should be an integral multiple of the wavelength. Okay, So what is the path length? Difference of path length. Okay, so suppose I start measuring the path. I'm measuring from here. Suppose this is A, the reflected ray is B, and this incident, this part is C, and this part is D. So the difference in path length of the first ray and the second ray till the point they combine, so the total length of path of ray 2 is C plus D, correct? C plus D. And the total length of path for first ray is A plus B. So A plus B is the path length of the first ray, and C plus D is the path length of the second ray. Okay, so the difference in path length, is the subtraction of the path length of first ray and the second ray. So this is the delta x. The delta x of these two waves which I have depicted here is C plus D minus A plus B. And if I assume that, or if these rays are falling at an angle of theta, and the difference in the distance between two successive crystalline layers is suppose D, okay, I am not going to prove it trigonometrically, but trigonometrically or mathematically you can prove that if the geometry is like this, where the distance is D and theta is, this is theta, okay, then we can prove that C plus D minus A plus B. I leave it as an exercise for you, but this doesn't fall, I think, in your normal course. It is sufficient to know that this path length will be equal to 2D sine theta. Okay, this path length, this path difference, the difference between these two paths, if you do some basic trigonometry, you will get that the difference of these path is 2D sine theta. Okay, so from this we know that for constructive interference, for the X-rays to be reflected back, okay, and not destroy each other, to be reflected back in a constructive way, so that they add up, for the X-rays to get reflected back, the condition is when the X-ray is falling on a crystalline solid whose crystalline, the distance between the crystalline layer is D, and the X-rays are falling at an angle of theta, the condition of getting a positive reflection back or a constructive reflection back, okay, having a constructive diffraction pattern, is 2D sine theta is equal to n lambda, and this is known as Bragg's law. Okay, so this completes our discussion on X-rays. I think it was a lengthy video, but we discussed lot of topics. None of those are new concepts. These are just the application of the concepts which we have already learned. So not a difficult chapter. So hope you understood and enjoyed the video. Thanks for watching.